Signal-to-noise ratio is a measure used in science and engineering that compares the level of a desired signal to the level of background noise. It is defined as the ratio of signal power to the noise power, often expressed in decibels. A ratio higher than 1:1 indicates more signal than noise. While SNR is commonly quoted for electrical signals, it can be applied to any form of signal. The signal-to-noise ratio, the bandwidth, and the channel capacity of a communication channel are connected by the Shannon-Hartley theorem. Signal-to-noise ratio is sometimes used informally to refer to the ratio of useful information to false or irrelevant data in a conversation or exchange. For example, in online discussion forums and other online communities, off-topic posts and spam are regarded as noise that interferes with the signal of appropriate discussion. Definition: signal-to-noise ratio is defined as the power ratio between a signal and the background noise, where P is average power. Both signal and noise power must be measured at the same or equivalent points in a system, and within the same system bandwidth. If the variance of the signal and noise are known, and the signal is zero mean. If the signal and the noise are measured across the same impedance, then the SNR can be obtained by calculating the square of the amplitude ratio, where A is root mean square amplitude. Because many signals have a very wide dynamic range, SNRs are often expressed using the logarithmic decibel scale. In decibels, the SNR is defined as, which may equivalently be written using amplitude ratios as. The concepts of signal-to-noise ratio and dynamic range are closely related. Dynamic range measures the ratio between the strongest undistorted signal on a channel and the minimum discernible signal, which for most purposes is the noise level. SNR measures the ratio between an arbitrary signal level and noise. Measuring signal-to-noise ratios requires the selection of a representative or reference signal. In audio engineering, the reference signal is usually a sine wave at a standardized nominal or alignment level, such as 1 kHz at +4 dBu. SNR is usually taken to indicate an average signal-to-noise ratio, as it is possible that instantaneous signal-to-noise ratios will be considerably different. The concept can be understood as normalizing the noise level to 1 and measuring how far the signal stands out. Difference from conventional power: in physics, the average power of an AC signal is defined as the average value of voltage times current. For resistive circuits, where voltage and current are in phase, this is equivalent to the product of the RMS voltage and current. But in signal processing and communication, one usually assumes that that factor is usually not included while measuring power or energy of a signal. This may cause some confusion among readers, but the resistance factor is not significant for typical operations performed in signal processing, or for computing power ratios. For most cases, the power of a signal would be considered to be simply where A is the amplitude of the AC signal. Alternative definition: an alternative definition of SNR is as the reciprocal of the coefficient of variation, that is, the ratio of mean to standard deviation of a signal or measurement. Where is the signal mean or expected value and is the standard deviation of the noise, or an estimate thereof. Notice that such an alternative definition is only useful for variables that are always non-negative. Thus it is commonly used in image processing, where the SNR of an image is usually calculated as the ratio of the mean pixel value to the standard deviation of the pixel values over a given neighborhood. Sometimes SNR is defined as the square of the alternative definition above. The Rose criterion states that an SNR of at least 5 is needed to be able to distinguish image features at 100% certainty. An SNR less than 5 means less than 100% certainty in identifying image details. Yet another alternative, very specific and distinct definition of SNR is employed to characterize sensitivity of imaging systems. See signal-to-noise ratio. Related measures are the contrast ratio, and the contrast-to-noise ratio. SNR for various modulation systems: amplitude modulation, channel signal-to-noise ratio is given by where W is the bandwidth and is modulation index, output signal-to-noise ratio is given by frequency modulation, channel signal-to-noise ratio is given by Output signal-to-noise ratio is given by improving SNR in practice. All real measurements are disturbed by noise. This includes electronic noise, but can also include external events that affect the measured phenomenon, wind, vibrations, gravitational attraction of the moon, variations of temperature, variations of humidity, etc., depending on what is measured and of the sensitivity of the device. It is often possible to reduce the noise by controlling the environment. Otherwise, when the characteristics of the noise are known and are different from the signals, it is possible to filter it or to process the signal. For example, it is sometimes possible to use a lock-in amplifier to modulate and confine the signal within a very narrow bandwidth and then filter the detected signal to the narrow band where it resides, thereby eliminating most of the broadband noise. When the signal is constant or periodic and the noise is random, it is possible to enhance the SNR by averaging the measurement. In this case, the noise goes down as the square root of the number of averaged samples. Digital signals. When a measurement is digitized, the number of bits used to represent the measurement determines the maximum possible signal-to-noise ratio. This is because the minimum possible noise level is the error caused by the quantization of the signal, sometimes called quantization noise. This noise level is nonlinear and signal-dependent. Different calculations exist for different signal models. Quantization noise is modeled as an analog error signal summed with a signal before quantization. This theoretical maximum SNR assumes a perfect input signal. If the input signal is already noisy, the signal's noise may be larger than the quantization noise. Real analog-to-digital converters also have other sources of noise that further decrease the SNR compared to the theoretical maximum from the idealized quantization noise, including the intentional addition of dither. Although noise levels in a digital system can be expressed using SNR, it is more common to use EBNO, the energy per bit per noise power spectral density. The modulation error ratio is a measure of the SNR in a digitally modulated signal. Fixed point. For n-bit integers with equal distance between quantization levels, the dynamic range is also determined. Assuming a uniform distribution of input signal values, the quantization noise is a uniformly distributed random signal with a peak-to-peak amplitude of 1 quantization level, making the amplitude ratio 2n/1. The formula is then. This relationship is the origin of statements like 16-bit audio has a dynamic range of 96 decibels. Each extra quantization bit increases the dynamic range by roughly 6 decibels, assuming a full-scale sine wave signal. The quantization noise approximates a sawtooth wave with peak-to-peak amplitude of 1 quantization level and uniform distribution. In this case, the SNR is approximately floating point. Floating point numbers provide a way to trade off signal-to-noise ratio for an increase in dynamic range. For n-bit floating point numbers, with n bits in the mantissa and m bits in the exponent. Note that the dynamic range is much larger than fixed point, but at a cost of a worse signal-to-noise ratio. This makes floating point preferable in situations where the dynamic range is large or unpredictable. Fixed-point simpler implementations can be used with no signal quality disadvantage in systems where dynamic range is less than 6.02 m. The very large dynamic range of floating point can be a disadvantage, since it requires more forethought in designing algorithms. Optical SNR. Optical signals have a carrier frequency that is much higher than the modulation frequency. This way the noise covers a bandwidth that is much wider than the signal itself. The resulting signal influence relies mainly on the filtering of the noise. To describe the signal quality without taking the receiver into account, the optical SNR is used. The OSNR is the ratio between the signal power and the noise power in a given bandwidth. Most commonly a reference bandwidth of 0.1 nm is used. This bandwidth is independent of the modulation format, the frequency and the receiver. For instance, an OSNR of 20 decibels per 0.1 nm could be given, even the signal of 40-bit DPSK would not fit in this bandwidth. OSNR is measured with an optical spectrum analyzer. See also. Notes. References. External links. Taking the mystery out of the infamous formula, SNR equals 6.02 n plus 1.76 decibels, and why you should care. 1. Analog devices, ADC and DAC glossary Maxim integrated products, understand SINAD, ENAB, SNR, THD, THD plus N, and SFD so you don't get lost in the noise flora analog devices, the relationship of dynamic range to data word size in digital audio processing, calculation of signal-to-noise ratio, noise voltage, and noise level, learning by simulations a simulation showing the improvement of the SNR by time averaging, dynamic performance testing of digital audio DA converters, fundamental theorem of analog circuits, a minimum level of power must be dissipated to maintain a level of SNR.